Hello and welcome back. It's time to implement Heap Sort using Java. I already have explained the Heap Sort procedure earlier in this section. Actually, I have explained everything about heap in this section, starting from the definition, how we can insert a new element into the heap, how we can delete the element from the heap, how we can adjust the heap if the heap is distorted, and then I have explained how we can build a heap from any arbitrary array using the heapify operation. And then I went on explaining the heap sort algorithm as well. So I did all of them earlier and I used visual description so that you can understand these things clearly. So I hope you have understood all these things clearly by now. If not, I'll strictly recommend you to get back to the previous lectures of this section and then come back here and to understand this heap sort implementation. Okay, in order to implement the heap sort, I have written a new class there. This is class heap. And we have this array as instance member of the class, and we are allocating that array here within the constructor of this class. You can see that the constructor is receiving the size of the array, and we are practically allocating one more than the size for the array. That is because we are not going to use the 0th element, and we are going to use from index 1 up to the size. So if you intend to sort 20 elements, then practically we are allocating 21 elements array, and the valid indices for that is going to be from 0 to 20, and we are going to use from index 1 to index 20. And here is the heap sort method that we are going to complete in this lecture, and here's the heapify that also we are going to write here in this lecture, and here is the adjust method that we are going to complete as well. The field random data method is just as the same. I've just copied that from the earlier class sort utility. The only change is here. You can see that I'm starting from I equals 1. And because we are not going to use the 0th index for heap. And here as well, you can see that I have copied this method print to console from the previous sort utility class, and it is also starting from I equals 1. And all other helper methods remain same. Only the difference is that we are starting from 1, index 1 for all of them. You can see that input from console is also starting from I equals 1. And is sorted, same here. Only the difference is that we are starting from I equals 1. And I have written the main method there. I will show you that later on. Let me just first complete the heap sort and heapify and adjust method. So we'll be doing them here. Okay, let's now go ahead and complete this adjust method first. The adjust method receives index I, that's the first parameter, and the second one is the total number of elements in the heap. Let's not forget that the index 2 times I, that's the left child of this index I, is a heap, is a max heap, and also the right child of this index I is also a max heap. We need to adjust the index I so that a max heap is maintained at index I, and that's the task of this adjust, if you have not forgotten. So we get the index of the immediate left child of that index I in the variable j, and then I declare a variable item and I get the content of the index I of the array. So we are going to place this item at the proper index so that the max heap is maintained at index I. Now we need to iterate in a while loop. So j less than equals n as long as j is valid. And immediately entering into the while loop, we need to check if this j is having a sibling or not. Now if j less than n, that indicates that j has a sibling. And also we need to check which one is larger, the current jth indexed element or the sibling of this. So for that, we need to compare array j with array j plus 1. If array j is less than array j plus 1, that indicates that j plus 1 is having the larger value. In that case, we will move j to j plus 1. That means we are actually placing j to the larger element of these two siblings. So j is right now, after this if, on the larger siblings that contains the largest of these two siblings, j and j plus 1. So now we need to check if the item is larger than this jth element or not. If that is so, we have found a place for the item, we are breaking the loop. Otherwise, we need to just move the current jth element to its parent. So we move this the current element to the parent. The parent's index is j divided by 2 and the current element is at j, right? So I have explained all these things with the visual description as I said at the beginning of this lecture. So if you are not finding this comfortable, this development, then I will strictly recommend you just to get back to the previous lectures again and then come back here and follow this. Okay, now we need to update j. We need to go to the left child of the current j and we need to continue with the same procedure. And after coming out of the while loop, we have found the position where we should place that item. So we get that position at j divided by 2 and we are placing that item there. And we are done writing this adjust operation. So we'll need a loop counter for heapify and we need the total number of elements in the array. That's actually array dot length minus 1. Let's not forget that we have actually allocated one more elements than the size of the array we need, right? So n is actually the size of the array or size of the heap. So here we go. So we'll start from n divided by 2 and it will go up to I greater than equals 1. And each time we'll reduce I by 1. And we'll adjust the index. So we are calling the adjust operation for adjusting the index I. And here we are passing the n. That's the total number of elements in the array. So the heapify is done. Now let's go ahead and write the heap sort. Okay, so we are done implementing the heapify and the adjust operation. Now it's time to implement the heap sort. At the beginning of the heap sort, we need to call the heapify operation just to build the heap from the array elements. And it's going to do that in linear time without using any extra space. And then we need to iterate in a loop starting from I equals n. N is the total number of elements in the heap. So we are just going to assign that in the variable n. Okay, so I'm declaring that variable n and assigning that with array.length minus 1. I greater than equals 2, it will iterate as long as I is greater than equals 2. And on each iteration, we are reducing I by 1. Then we need to get the content of the root, that's the largest element. So here we go. The array 1 is the root and we are taking that out of that index 1 and assigning that to the temp variable. Now we are going to copy the last element to the root. That's what we do for deleting an element from the heap. We actually take out the content of the root and then we copy the last element to the root. And as I said, I already have explained these things to you earlier. Okay, so we take the last element and copy that to index 1. Now we need to call the adjust operation. Because the heap is no more a heap because we have copied the last element to the root, so heap has been distorted. So we need to adjust the index 1 and the total number of elements is I minus 1 because I is currently, we are starting from I equals n, right? That's the total number of elements in the heap. Now we'll be reducing one element by deleting the heap on each iteration. So since we have taken out one element, so the total number of elements in the heap right now is I minus 1. And finally, we are going to place that temp, that the largest element at index I, and we'll iterate back into the for loop and we'll do the same thing again. So that's how we actually do the heap sort. And finally, we are returning the elapsed time, the end time and start time. That's as usual. Okay, here is the main method. The size is 20 initially and we are creating the heap object. That means the object of this class with this size 20. Let's not forget that it's going to allocate 21 elements. And then we are filling the array with random integer data by making a call to that fill random data method. And then here we are actually going to call the heap sort. You can see that, right? I'll just print the elements into the console for the first time for these 25 elements. Later on, we'll comment out all this printing and we'll go for larger number of elements. So let's go ahead and run this for size equals 20. Let's check this. So here we go. This is the unsorted array. You can see that there, and it has been sorted in ascending order. And here's the sorted array. It's working fine. It looks good. So now what I'm going to do, as usual, I'm going to execute this heap sort for various different input sizes, and we are going to note down all these execution time for all those different input sizes, and we'll try to plot them in Excel. So I'll start with 10,000 numbers, and this time I'll not print all these data onto the console, because printing 10,000 numbers into the console and viewing them is going to be insane, right? That's going to take huge amount of time. So I'm just commenting them out. Now it's going to test whether the array is sorted or not by using this is sorted. Okay, so here we go for 10,000 elements. You can see that for 10,000 element, heap sort took 5 milliseconds. And this time I'm going to note down that 5 milliseconds here for 10,000 elements. Now I'm going to do that for all of these input sizes, for all these different input sizes. And I'll get back to you once that's done. I'll pause the video meanwhile. Okay, I'm done. You can see that these are the execution times in milliseconds for each of these input sizes. The maximum that I took was 100 million numbers, and that actually sorted in 41 seconds, 41.611 seconds. So that's amazing, right? So let's go ahead and plot this. We are interested in finding the n versus fn graph, and the expected solution is big O of n log n. Okay, here it is. It's interesting. You see that when the n is large, it's almost straight line. That's amazing performance of heap sort. Now when the n is small, here's a little bent upward, but rest of the time it's actually straight line there. So it's well below n log n. We can say that it's big O of n log n, no doubt about that. So that's how the heap sort works, and here is the file that I'm going to attach with this tutorial. You can download it and can examine it by yourself, but I'll encourage you to write it by yourself before using my file. Please try to write down the procedure by yourself after understanding the algorithm in the previous lectures. I hope you can do that by yourself. Thank you for watching this.